As you may know, different reactions that are equilibrium reactions go to different extents. So some reactions, for example, this reaction, form large amounts of products compared to reactants. There's still a little reactant left, but there's a lot of product. On the other hand, there's some where the amount of products and reactants is appreciably similar. So they're both about the same. While yet other reactions have significantly higher concentration of reactants compared to products. So only a very small proportion of reactant molecules get converted to products. So what we want to do is to find a way to quantify the position of equilibrium for a given reaction. We want a number that tells us if the reaction goes to products, which means it goes far to the right, or does it go towards the reactants? Does it stay mostly as reactant and only a little goes to products? It stays on the left hand side of the equation, right? Or is it in the middle? Do we have about the same amount of reactant and product? To do this, we use the equilibrium constant, and we can show that for a given temperature, the equilibrium constant, at least for purposes at this level, remains the same at all concentrations that you're going to be dealing with. And the equilibrium constant is basically the concentration of products over the concentration of reactants. This is called Kc. You'll learn about a different way of expressing equilibrium constants a bit later. In this case, Kc, we're expressing it in terms of concentrations, all of them in terms of molarity, moles per liter. One thing you should know, however, is that whenever you're writing the expression for the equilibrium constant, you should be raising each concentration to the power of its coefficient. This makes sense from the perspective of saying I can write this right hand side, for instance, as NH3 gas plus NH3 gas. So I can just multiply these two concentration terms together, which means that I'm just squaring it. So the equilibrium constant for this reaction is therefore product, so NH3 squared, this 2 here, comes from the reaction coefficient divided by the concentration of N2 divided by the concentration of H2 cubed, because we have a coefficient 3 here, so we have this coefficient here. So let's try and do this numerical problem. Consider the reaction of two molecules of nitrogen dioxide reacting to form, in an equilibrium process, dinitrogen tetroxide. And at equilibrium we have these concentrations. So first we need to write out the expression for the equilibrium constant, Kc. Kc is equal to the concentration of N2O4 divided by the concentration of NO2 squared, which is equal to, if I plug in the numbers here, the concentration of N2O4 is 0.00140 molar divided by the concentration of NO2, which is 0.0172 molar, all squared, which is equal to 4.72. You should note that equilibrium constants have no units. So what does the equilibrium constant actually mean in terms of the position of equilibrium? Now, as we can see, the equilibrium constant is equal to concentration of products over reactants. So, if the position of the equilibrium lies towards the left, it is favoring the reactants, then we expect to have a lot more reactants than products. So we have a small number on top compared to the bottom number. So small divided by big gives me a small number, much less than 1. So if the equilibrium constant is small, then we know that reactants are favored. Conversely, if the reaction goes largely to completion and the products are favored compared to the reactants, then as you can see from here, the product, the numerator, is much bigger than the denominator. So big number divided by small number gives me a large number, and the equilibrium constant will be much greater than 1.